All right, gang, the purpose of this video is to demonstrate the calculation of the mean square between a mean square within. And I always hesitate in a grad level class to demonstrate this, but yeah, you know what, it's not going to take that long and it might help someone clear up a few things. So the data set that I'm going to use is one that I've used previously. Apparently we have three professors, Professor A, B, and C, and we have some quiz scores out of 50 points possible. We have a balanced design, which means that uh, we have equal sample sizes for each professor. And you can see over in R that I have inputted the data a little differently, but that's just the way I did it. I don't know, whatever. So let's get here. So the game plan is to show the calculations. The very first thing that we'll need is we'll need the grand mean. So I think the easiest way to do that, I'm just going to call that GM, is to take oh gosh, I don't even know. I guess the mean of A plus the mean of B is probably an easier way, but I just don't even care about uh, exploring that right now. I've got bigger fish to fry, right? Now I can only use this method. I can only average the means of A, B, and C because I have equal sample size. If we didn't have equal sample size, then we'd have to explore the sum of each and divide by the total sample size. But again, something that should be pretty easily done for math grad students. So the grand mean here is 35.59, 33.60. So first thing I want to do is I want to do a calculation of the sum of squares between. So the sum of squares between is going to be the sample size. I don't even know what the sample size is. So it's 9. Okay. So sum of squares between is going to be 9 times the mean of A minus the grand mean, quantity squared. And if I have to do this, type out all this, I'll lose my mind. So I'm going to do this because I don't want to lose my mind. It works nicely when we have a balanced design. It's a little bit more complicated because of some things we have to do in R if we don't have a balanced design. So anyway, there's the sum of squares between. So sum of squares between will be 626.74. Now, when we calculate or present the results from an ANOVA techniques, we typically present them in a table. So you can see that we have our source, between, within, and total. Now the R output will look a little different. This is the, I think this is the one used by SPSS and SAS. Really R, SAS, and SPSS are the only three that statistical software packages that I've used very much. I've used Jump a little bit, and I've used StatCrunch, but not a lot. So I know that the sum of squares between is going to be 626.74. I believe that's, let me circle back to that. I believe R actually will state the factor name. So, and this is probably going to be scores. And then the within, they probably use this, list this as residual. So just keep that in mind. Degrees of freedom, K minus 1. So we have 3 professors. So degrees of freedom will be equal to 2. Sum of squares within. It's going to be very easy to calculate. We're going to have n minus 1. So we'll have 8 times the variance for A, right? Actually, I should just just do this. So sum of squares within is 893.78. And the degrees of freedom within will be our total sample size. So if we have 9 in each, we have 27 minus 3 groups. So there's going to be a 24 degree of freedom there. We would want to get our sum of squares total. And that's just going to be the sum of squares within plus the sum of squares between. So that's 1520.52. And we leave these two blank. I'll explain why in just a second. So the mean square between is easy to find. It's just going to be the sum of squares between divided by the degrees of freedom. So 313.37. And we'll have the sum of squares within divided by 24 is 37.24. Now, what happens? We leave this blank for a reason. If I take, for example, the total degrees of freedom, which would be equal to 26, and if I take 1520 divided by 26, I get a number. That number will not be equal to the mean square between, the sum of the mean square between and the sum of the mean square within. So for that reason, these two entries are left blank. Now, to find the F statistic, we just take the mean square between divided by the mean square within. And we get 8.41. Now, what I'll do in your homework assignments is I'll give you partial, and on your exam as well, I'll give you partial tables where you have to come in and, fill in the degrees of freedom or sum of squares, whatever it may be. And I'm sure calculate a test statistic and a p-value. But it's easy to fill these out. Once you get the sum of squares between and within, divide by the degrees of freedom to get the mean square, divide these two to get the F statistic, and then you can use R. The following way to get the p-value. So I would just go 1 minus because I need the area to the top of 8.415 with degrees of freedom to 24. So our p-value is going to be 0.0017. Now, if I were going to report this, I would report it as F2, 24 with a test statistic of 8.41. And reporting this appropriately, it's almost less than 0.001, but not quite. So the level of statistical significance that we would report here would be less than 0.01. Now, as you might imagine, we can make these same calculations using R and not making all of these hand calculations. I'm always afraid when I do hand calculations that I'm going to take 2 plus 5 and get 9 or something goofy. I remember Dr. Hammonds. He was my advisor in undergrad, and he told me something one time that turned out to be true. He said, Doug, the further you get in mathematics, the higher level at which you learn, you're going to lose your arithmetic skills. And gosh, was he accurate with that. All right, gang, the first thing we need to do to get this data set in a format that we can use ANOVA techniques in R is to get this. Now, remember back in lesson 1, I said the data set that we desire, this should be tattooed to your brain. When we read left to right, all of the information on that particular line is specific to one case, one person, one tree, one dog, one cat, one school district. When we read vertically, we have our variables. Okay, so the first thing I would probably want to do is just create something. I'm just going to call it new data because I'm not that clever with naming things. And I would create a new data frame, and I would bind or kind of mash together the variables A, B, and C, which are the professor scores. But when I do view new data, I can see that I don't have the data set in the format that I want, because when I read from left to right, that 32 and that 29 and that 27 is not specific to one student. So I can easily take care of that. I'm just going to call this new data set. I'm going to create data, and I can just stack my new data. And when I get data, you can see that I get it in the format that I want. Again, come down to the 18th case. When I read left to right, I know that I have one particular student, information on one particular student who happened to be in Professor B's class and scored a 12 on the quiz. Now, once I get in this form, conducting an ANOVA is really, really easy. We have the AOV command. The first thing we'll put is our factor score, which for this example is values. And the next thing we do, input is our independent variable, which is always our categorical variable, which in this case has been classified as independent. Just make sure there's no misunderstanding here. I'm going to tell R that the data set I want this executed on. So if I go summary model, you can see that the information to the left lines up with the information on the right. Now, just a couple of things to point out. First of all, in R does not give us a total line, but come on, getting the totals is very easy. Also, it names the source between as IND, which is the name of the categorical variable. And instead of within, it labels that residual. So again, that's just something you have to tattoo to the brain and appreciate that. It seems like to me that if you run, I'm probably going to regret doing this, but I thought if you ran, yeah, hmm. Okay, whatever. There used to be some commands in the older version of R that would actually give you your total line. And again, it's not the major uh, to be asked to add the sum of squares to get the sum of squares total. But there is a way, and I forget what it is because they've switched this stuff around to actually get an output with the sum of squares total. One other thing to notice, not a big deal. They place the degrees of freedom first. I always place the sum of squares first. So just tattoo that one to the brain too. All right, moving forward, what are we going to do? Well, our focus is going to be on testing assumptions and examining where we have statistical significance. Because again, what is the null hypothesis here? The null hypothesis is that the mean for Professor A is equal to the mean for Professor B equal to the mean for Professor C versus our H sub A at least, and I'm not going to write this out because I've written it out before, but at least one pair of means is statistically significant. Now, which one is it? Well, we have to run what are called post hoc analyses to determine that. But I can get an indication using A, B, and C. Now, if I didn't have that, what I would have to do is probably do a T apply uh, and just do my values over my independent variable mean. Hmm. Oh, don't you love it when this happens? All right, so we had to attach the data. So the reason I was able to run mean A, mean B, and mean C here is because I have this command right here where the data has been entered. Typically, we won't have that. Typically, we'll just have our data set in this format. So obviously, if I ran this command with the data in this format, I wouldn't get anything. I would have to run the tapply. And because I didn't attach the data set, I couldn't run the means on the values across each category. So when I view that, it looks like to me that I'm probably going to get statistical significance between Professor B and A and Professor B and C. I doubt that we'll have statistical significance between Professor A and C, but you know what? That's just something that we'll have to explore in the next video. All right, gang, that's all I got. Take care.